Hello, and today I will solve one physics problem on RC circuit in direct current using the computational thinking approach. And I will explain my solution using the Prada steps. First is decomposition, pattern recognition, then abstraction and algorithm design. And also I will use graphs to support my explanation. So this is our example. It's a problem about measuring capacitance. And in this problem, a capacitor is first charged to 9 volts and then it's discharged through a resistor of 25,000 ohms. And we're giving voltage values at different times. And we need to determine the capacitance and the current after 5 seconds. So first I use decomposition and I break the problem into smaller parts. I identify what is given and what I need to find. What is given? Resistance. The initial, it's 9 volts and the table. Also we have the table here with the time and the voltage. We will use it in the future. And what we need to find is C and also it's after 5 seconds. So instead of thinking about the whole problem at once, I split it into 2 smaller tasks. And first, find the time constant and capacitance. And the second, use that result to calculate the current. And that was the first one. So the second one is a pattern recognition. I recognize that this is a standard capacitor discharging problem in an RC circuit. In this kind of problem, the voltage doesn't not decrease linearly and it decreases exponentially. So the standard form is, let me write this. And where the time constant is this one. So I already know the general behavior, the voltage, charge and the current all decay exponentially with the time. The next, I use abstraction and I remove details that are not necessary for solving the problem and let me write them some important resistance, the voltage, and this one. So for example, I don't need to focus on the physical appearance of the circuit or extra details about the switch. I only keep the essential variables, the resistance, the voltage, the time, and the time constant. This helps me focus on the mathematical model of the discharge process. And finally, I use algorithm design. I create a sequence of steps to solve the problem, and my plan is the first. Use discharge equations, then linearize with a logarithm, find the slope, find time constant, compute capacitance, and compute current at 5 seconds, after 5 seconds. First, for a discharging capacitor, the voltage is given by this formula. And here our V initial is 9 volts. And the T is the time constant that we need to determine. After that, To make the relationships easier to analyze, I take the natural logarithm of both sides. And then I get logarithm b is the initial. Oh, sorry. And this is in the form of straight line. And the form of straight line, we know this one. So if I plot logarithm v versus the time, I should get a straight line. Its slope will be 1 over this one. And also I add two graphs. The first one. The first graph shows the physical behavior of the capacitor voltage over time. So it starts at 9 volts and decrease exponentially towards 0. And the horizontal axis is the time in seconds written as t, and the vertical is v. About second graphs. The second graph is more useful for calculations, and I plot logarithm v versus time. So the horizontal axis is also the time, and the vertical axis it's logarithm v. Because the equation is linear in this form, the graph becomes a straight line, and the slope of this line is equal to -1 over time constant. And after that, we need to find time constant. So in the book, the slope value is given. We have this value, 28 seconds. And substituting the slope value, our time constant is equal to -1 divided by -0.28. So it will be about 3.6 seconds. Yeah, this is our time constant. Now we can compute capacitance. I can determine the capacitance using the formula. So our C is time constant divided by resistance. And substituting the values, our capacitor is second dividing by 25,000, and this giving 1.44 multiply which is 140 microfarad. So the capacitance is approximately this. Then we need to find initial current. And at the beginning of discharges, it's the initial equal to the initial over resistance. So our E initial is 9 dividing by 25,000, and this gives to 3.6 multiply or yeah, let me write. So yeah, we find it this value. This is our initial current. And now we can find the current after 5 seconds. So the current also decays exponentially with the same time constant. So I'm using this formula, is E initial E over, and substituting the values we already have this one. So the 5 seconds over 3.6, and after calculations we have I get the current is 90. Yeah, so the current after 5 seconds is approximately 90 microamperes. And now we can move on to our simulation. We have the initial values, and we can start. At first, we have initially the capacitor is charged to 9 volts, and after that we can switch. When we're switching, right after switching to the discharge position, the current is about 360 microamperes, which matches to theoretical initial current. That's good. And then we waiting for our time constant. And here, after 3.6 seconds, we see that our voltage drops to about 3.3 volts, which is 37% of the initial value. Then after 5 seconds, we see that our current is about 90 microamperes. That's right. And to summarize, I solved this problem using the computational thinking through the Prado steps. In decomposition, I separated the problem to smaller parts. In the second, I recognized this as standard RC discharge problem. In abstraction, I focused only on the essential variables. And finally, in our algorithm design, I followed the clear sequences of steps. We have our plan. And as a result, I found my answers, and now I will write them. And at first, our time constant is 3.6 seconds. Our capacitance is about 100 microfarads. Our initial is 36 microamperes. And current after 5 seconds is about 90 microamperes. So that was all for today. Thank you for your attention. Goodbye.